Everybody, we're now on our next video on number theory, and in this video this should be watched upon after the video on greatest common divisor, the GCD. So we're now on the topic of linear combination. So what is linear combination? So a linear combination of the integers a and b, okay, integers a and b, so they are both integers. So this is an integer, um, this is also an integer, okay, is the sum, okay, take note, sum of the multiples of a and b. That is the sum of the form alpha a plus beta b. So this is a and b, so multiples where a and b, alpha and beta rather, are integers. So multiply this a by some integer alpha, multiply this b by this some integer beta, and then get the sum of the multiples. So that's what we call a linear combination. Okay, pretty much straightforward there. So for example, so we have 2 times 3 plus 5 plus 7. So a here, you can imagine this is alpha, this is a, this is beta, this is b. So we have a as 3, b as 7. So we multiplied the 3 by 2. Okay, this is a multiple of 3 then. We multiply the 7 by 5, that's a multiple of 7. So this is what we call a linear combination of the integers 3 and 7. So we call this a, we call this a b. So also, we can change that, okay, as another linear combination. So this can be this is still a and b, but this is another alpha, this is another beta. Yeah, but still, it's a combination of 3 and 7, a linear combination of 3 and 7. So pretty much that's the concept of linear combination, okay, of two integers a and b. Okay, it's just the sum of multiples of these integers a and b. So I'm going to give you a theorem here, pretty much a strong theorem that will lead us to our concept of Euclidean algorithm. So this theorem is from Euler. This was a theorem by Euler. So it says that for all a and b in the positive integers in the natural numbers, so imagine a and b to be positive, strictly positive, the GCD of a and b is a linear combination of a and b. Okay, again, the GCD, the greatest common divisor of a and b, is a linear combination of a and b. So we'll be saying a proof here about this theorem. Okay, we'll be proving that. So let's put a proof. So first off, we let this set S, okay, to be the set of the linear combinations of A and B, which is strictly positive. So be the set of positive linear combinations of A and B. So we say by the well ordering principle, um, or rather, that is not yet here. I'm too excited. Okay, so again, let S be the set of positive linear combinations of A and B. So that is we say that S is equal to the set M A plus N B, okay, such that M A plus N B is greater than 0. Okay, and that M and N are in the integers. Okay, so we have MA and NB. So we imagine M here and N as the multiples that we want to multiply it to get the multiples of A and B. And we say that it's strictly greater than 0, and that they are integers. Okay, so we want to first show, okay, after this proof, to show that S has a least element. This is where we will apply the well-ordering principle. I'm sorry, has a least element. Okay, we say that since a is greater than 0, a is positive. Since we know it here, a is positive, so it's understood that it's greater than 0. So since a is positive, okay, so we say that the least number that a can have is 1. Okay, 1 times a plus 0 times b. So this is your a, this is your b, this is your alpha. This is your beta, for example, or shall we say m and n. Okay, so we can have this value a as equal to 1. Okay, so therefore, this a is still, this value of a, which is a equals 1, times a plus 0 times b, is a part, okay, or in the set of integers in S. So therefore we say that S is non-empty. Say is S is non-empty. Okay, so after that, by this is it. Okay, so by the well ordering principle, since it's non-empty and it is composed of positive integers, S has a least element, and we will call it element, shall we have it as D. Now then we would like to show, oops, sorry. So okay. Um next is we would like to show, so to show that D, this least element D here, okay, is equal to the GCD, okay, is equal to the GCD of A and B. Okay, we say that first, since D belongs to S, therefore it is in the form of D equals alpha A plus beta B. Okay, so it's in the form. Okay, for some um integers A and B. Okay, so first we will put this in two parts to show that the D is the GCD is equal to the GCD of A and B, since that is what we want to show in the theorem. Okay, and okay, let's start. Let's have the first part. So the first part says that first we will show that D divides A, D divides A, likewise D divides B. Okay, so if this happens, so by the division algorithm, by the division algorithm, there exists some integers Q and R such that A is equal to D times Q plus R, where R is strictly less than D, but R can be equal to 0. Okay, so what we will do is to substitute, okay, substituting for D, what we have is R, this R here, I want to get the R is equal to, transposing this dq to the other side, A minus dq, okay, the value of D is shown above. D is equal to this, alpha A plus beta B. So let's do that. This is equal to then A minus D is alpha A plus beta B times Q. Okay, and then what do we have? Okay, we're going to put it strictly as it is. So let's put it straightly. So A minus alpha A minus beta B. Okay, and this will have the Q here. We'll have the Q here, and beta B Q. So what we did is we distributed. Okay, if you want to see it, we distributed the minus sign to both terms while distributing the Q to the both terms. So we have alpha AQ minus beta BQ. Okay, furthermore, we can see that it can be written as this. So your R can be rewritten as, okay, getting the common monomial factor here in A. So what we have is 1 minus alpha Q. A can be written here, but I chose to put it here. It's still the same. Okay, and then plus, why is it plus? It's minus. Let's put the minus sign here. Beta Q by commutativity times B. Okay, so what do we have? In short, if you want to put it in a single straight line, so we say that R is equal to 1 minus alpha Q times A plus minus beta Q times B. So we can see here that it is actually in the form of, recall that the linear combination must be in the form of something like alpha A plus beta B. So only that here, the alpha in this part is somehow different. It's not strictly as an alpha. So this is your alpha here. And this is your beta over here. So this is my beta. So you can see that R, okay, this shows, therefore, by this part here, okay, shall we say, this shows, this shows, um, this shows R, okay, is a linear combination of A and B. Okay, so therefore, if we say if R is greater than 0, so then we say that R is part of S. Okay, but since we see that R is strictly less than D, okay, so that is R is less than the smallest integer or smallest element in S, because we say from way above here that D is the least element, but then we can see, since this is true, meaning this statement holds. That's true. Okay, so meaning we say that R is strictly less than D. That is to say that it is strictly less than the smallest element in S, which is of course a contradiction. This is a contradiction. Okay, so that cannot be done. It's a contradiction. It's less than the least element in D. So S, in short, R cannot be greater than 0. This is the point here. R cannot be greater than 0. Instead, R must be equal to 0. It should be equal to 0. So thus saying, thus, since that's the least, okay, that's the least that R could have. And since thus what we can say is A, since R is equal to 0, so what we have is A equals DQ. Where did we get that? We first say that, if you can remember, A is equal to DQ plus R. So since we said that R is equal to 0, so thus A is equal to DQ. And thus, if this statement holds, so we say that, so, yeah, D, so we say that D divides A. Okay, so yeah, we can see that D divides A. This is from our number 1 that we want to show that D divides A. Okay, D divides A. And showing D divides B is of the similar pattern actually. Maybe you want that as an exercise. You can also do it yourself. But for here in this video, for the purposes of this video, we'll not say that very strictly. But shall we say similarly, by similar arguments? Similarly, if D divides A, so therefore by the same argument, D divides B also. So thus, okay, thus D is a common divisor of A and B. Okay, so meaning D is a common divisor of A and B. So that's we showed that D divides A and D divides B. So that's the first one that we want to show. D divides A. We got check there. We got correct there. So yeah, this is a check and this is also a check. Now for number 2, we want also to show that that any positive common divisor of that something, okay, of A and B is less than, strictly less than, or equal to D. So maybe this is number 1. Let's put it parallel to it. Let's put it here for number 2. Oops, there's no space. Anyways, yeah, I'll try to fit it here down below. And then, yeah, we'll see what we can do. Okay. Now, for number 2, the second one that we want to show, okay? Now, we want to show that any positive, show that any positive common divisor, we will call that D prime. Can't fit. Let's put it here. Um, Maybe we can, you know, let's try to find ways here. Okay, so let's put it as, okay, size 2. Let's write it again. To show that any positive common divisor, okay, we'll call that common divisor as D prime. So the to any positive common divisor of D prime of A and B is strictly, not really, less than or equal to D, not strictly, less than or equal to D. So we want to show that. So we say, since D prime divides A and D prime divides B, then by theorem 3 from our videos, theorem 3, you can just search it on my YouTube channel. There's a theorem 3 called there. So by theorem 3, we say that D prime divides alpha A plus beta B. It's a linear combination. So that is, since alpha A plus beta B, recall that this is equal to, D is equal to alpha A plus beta B. Recall this one. So therefore, we say that is D prime is a factor of D. So if D prime is just a factor of D, so we say that D prime is less than or equal to D. Okay? Thus, by parts 1 and 2 of this proof, we can say that D is equal to the greatest common divisor of A and B. Okay, so this is our end of proof. Put it here. Okay, so that's it. By parts 1 and 2, D is a greatest common divisor of A and B. So therefore, we prove that the GCD, the greatest common divisor of positive integers A and B, is a linear combination of A and B. So therefore, the theorem holds. Okay, the theorem by Euler holds. Okay, so for all A and B in the positive integers, the GCD of A and B is a linear combination of A and B. So yeah, that's it for this video. Thank you very much for watching. It's quite a long proof, but yeah, we finished it. We managed it. Okay, so I hope you would like and subscribe, and see you soon for more videos. Okay, thank you very much.